Okay, a slightly more complicated example would be to think about the steady flow in a more complicated geometry, such as I've shown here, where we might be thinking about flow past a cylinder. And in particular, we're going to be thinking about a slow flow here, and this is what's known as Stokes flow that we'll define later on in the class. But the first thing you might notice from this is you can't really tell if the flow is going from the left to the right or from the right to the left, because in fact, everything is symmetric. So you can see our streamlines are symmetric. But you can see that material elements are certainly flowing past our cylinder. The streamlines are coming together in places, and we know that there's a fixed amount of flow between any two neighboring streamlines. And so material elements along here are certainly accelerated as they go around the body. They're stretched and rotated and translated. And so all of the different components that we've thought about are going to be in this. So this is known as Stokes flow after this gentleman, Sir George Gabriel Stokes, who was an Irishman who is responsible for what we call the Navier-Stokes equations that we'll get to later on. And then the flow was further analyzed with some important corrections made by a German, Wilhelm Oseen, that we'll also learn more about later on. So let's look at what this flow looks like. So here's our streamlines that we had, that I showed in the first page. And then here is a streak line visualization of those streamlines. And if you're interested in looking at a nice movie of this, then there's a YouTube link here. Now there's a mathematical equation for these streamlines, which I won't show you right now, but instead what we'll do is we'll actually try and evaluate those lines, and we're going to break down the velocity field into these three different components that we have. So here's our streamlines from the mathematical solution, and then on the top right we're going to have a material element, and we're going to focus on the deformation of this material element. And this material element is going to flow in from the left to the right, and we'll think about what happens. And so we'll remember that our velocity gradient tensor can be broken down in 2D into these four components. And we're showing that with both the stretching terms, which are shown in green, and the shearing terms, which are shown in blue, and the rotation terms, which are shown in pink. And so as our material element, which is a finite size, flows in and past this, you can see that the material element is both stretched and rotated and also sheared as well. And so our material element, when it exits the domain, actually has been substantially deformed. We'll play that one more time, just so that we can look at it again. So as our material element flows in, you can follow the red line, and you can follow the individual components that look like both the rotation in magenta, or what we've called the vorticity, the shearing deformation, which is shown in blue, which is our strain rate, and then also our stretching deformation, which is shown in green as well. And so again, we can see that there's a stretching, a rotation, and a shearing in this material element. And we now understand how the individual terms of our velocity gradient tensor are related to that.